Hi everyone. This is our look at the ideal gas law. Ideal gases are only hypothetical. They don't actually exist. They have two behaviors that separate them from real gases. Ideal gases don't condense when cooled. This just means that as the temperature drops, the gas is not going to become a liquid. We're not going to have trick questions where if the temperature drops, the answer is never going to be, oh, it turns into a liquid. Ideal gases don't condense when we cool them down. In addition, the molecules are not attracted to one another. There's no type of cohesive forces in between different gas molecules in the ideal situation. This is in contrast with real gases. In the real world, gases do have these two behaviors. Real gases do condense, and real gases do have these attractive forces between the particles, between the molecules. For us, we are only going to work with ideal gases, and there's a formula for us to do so. It's PV equals nRT. This is our most demanding formula so far because the units are quite specific. Here, the pressure must be in kilopascals. It's very unlikely that a question would even give us atmospheres or regular pascals for that matter. We're going to be working exclusively in kilopascals. The volume must be in liters. Just like in the molar volume formula in Avogadro's law, there the volume must be in liters. Here the same. It is going to be a commonplace thing for a question to give us milliliters, and we'll need to convert it. N is moles, nothing more to it than that. And R, this capital R, it's the ideal gas constant. It has a specific value, 8.314, and these complicated units, kilopascal liters per mole Kelvin. If we're using the ideal gas law, we're always going to use 8.314 as the value for R. It's a constant. Temperature, T, here we must have Kelvin. Big reminder, anytime in the whole course, if we're using temperature, it has to be in Kelvin. We're going to take our degrees Celsius and add 273.15 to make that conversion. We're going to do that all the time. Because the formula is normally set up as PV equals nRT, we're always going to need to manipulate it, whether we're solving for the pressure, the volume, the moles, or the temperature. Ideal gases don't really exist, they're only hypothetical. So the formula here and our work with them, it's all about making predictions. Sure, it might not be perfect because it's only theoretical and not real. However, it allows us to make predictions about behaviors and conditions at which we can find gases. The final thing to say is that just like the molar volume formula, our work with the ideal gas law just represents a snapshot. It's not a before and after like we saw with Boyle or Charles. This is at a discrete moment in time. There's a specific pressure, volume, temperature, and number of moles. And I hope that helps.